So hey everyone, this is Thai speaking right now. I'm a PhD student from the Computer Science Department of Tsinghua University. On behalf of our team, today I will introduce you to our ICPP 2020 paper, called a Congestion-Aware Request Dispatching Scheme for Replicated Metadata Server Cluster. First, before we dig into CARD, I will spend a little time talking about massive-scale machine learning training in product environments, which is a typical scenario for applying our method. I'm sure we can all feel it that many machine learning applications such as face recognition and all kinds of feeds and recommendations are becoming parts of our way of life. However, behind the scenes, all those improved user experience are mostly driven by huge datasets. Big companies often use multiple machines and hourly collected user data to periodically train an offline model for online inference. With the growing order of magnitude of data, the training scales also increase on, and the underlying data rate pipeline is facing great challenges because of this. Not only the workload is extremely stressed, but the cache-unfriendly random read pattern is also an annoying pain point. Generally, the training workers are interacting with an underlying distributed file system, requesting file metadata from a single metadata server, and fetching file objects from several data nodes, or we can call them the object storage devices. As mentioned before, the required computing resources are growing along with the model and the datasets. Within this context, when there are hundreds or thousands of machines in a cluster, a file fetching request starts to be blocked at the metadata access step. This could really prolong the whole training process, and the continuously arriving requests could further stress the metadata server and cause a single point of failure, which is a big potential threat to the availability of the whole system. To deal with this, the metadata service layer also needs to scale out in response, which also raises several new concerns to be addressed. How many servers do we need? How to achieve higher overall throughput while maintaining runtime stability? What if the server's capacities are different or shifting? We believe that all these concerns can be reduced to one goal, that is to make each server bear the load which is commensurate with its performance. In other words, if we balance the load, not absolutely but relatively, then all these problems might be solved at once. To achieve this goal, introducing a middle layer load balancer is a popular and common method. In addition to great global load balancing, many additional features can be integrated at the same time. However, to get a whole picture of the whole system continuously, this strategy does require extra computing and network resource. In the same time, all those heavy loads are falling on the load balancer as well. When facing heavy workloads, this is not a good solution. All the old problems remain, they just merely shift to this new load balancer. In that case, why don't we try the client-side solutions? We know that the workloads are coming from the clients, therefore it may be a good idea to address the problem where it happens. Not only that, compared to the server-side strategies, the client-side solutions can also be really cost-effective and easy to implement. So we have every client see things only from its perspective. The most straightforward client-side solution is the round-robin dispatching scheme. It is simple yet effective in homogeneous environments. Requests are routed to all servers in turn. First go to server 0, then to server 1, 2, 3, and go back to server 0, evenly and constantly. This means round-robin is not able to react to any runtime system conditions. It is fixed and inflexible. Another solution to this problem is to enable client-side heuristic selection. For instance, a lower latency-oriented method. Requests are always sent to the server with the lowest moving average of response time. When facing lightweight workloads, this is a great strategy for it helps the clients acquire a better quality of service. However, under heavy workloads, all the heuristic selection-based methods lead to severe herd behaviors and load oscillations. At this moment, all requests are routed to server 2. At the next moment, they are all sent to server 1 instead. This shifting goes back and forth and evolves into significant load imbalance. So, is there any compromise choice between round-robin and heuristic selection? Previous work called LAS used a preset threshold to mark the servers with the higher moving average of response time as congested. In brief, this solution can be considered as round-robin with throttling. When the load is lightweight, all requests are sent in a round-robin fashion. However, when the load is stressed, there is actually not much difference between this method and heuristic selection. For example, we assume that the threshold is set to 50 milliseconds. According to that, all requests will be routed to server 2. After a while, maybe all requests will go to server 0 instead, even though there is a throttling mechanism. Still, significant load imbalance remains, and it degrades the overall performance. To tackle this problem, we propose a new client-side solution, which turned out to be efficient for both homogeneous and heterogeneous setups. The main idea of CARD is to enable adaptive congestion-aware request dispatching at clients, which is inspired by the qubit algorithm for TCP protocol. If no congestion is perceived, then CARD grades to vanilla round-robin, but when a congestion happens at one server, the requests are not blocked. They are redirected to another underloaded server, if and only if all servers are considered overloaded from client's perspective, then the request will be suppressed. This is the overview of the congestion-aware rate control mechanism of CARD. As we all can see, there are several modules to be implemented. Let's skip the round-robin selector and the pending queue. The most important parts are the rate limiters and the feedback module. This feedback module is in charge of taking in replies from servers and dispatching processed feedbacks to the rate limiters. As a response, the rate limiters adapt the sending rate accordingly. But what happens exactly in the rate limiters? Basically, each rate limiter can be regarded as the agent of each server in the process unit. The rate limiter for server 0 will restrict the number of requests routed to server 0 per delta time window. The restriction is not fixed. It will increase dynamically according to a qubit growth function, which I will address later. As for the feedback module, besides forwarding replies, it counts and computes the receiving rates for all rate limiters. To realize congestion-aware rate control, I think we have to figure out how to identify a congestion event first. Assume that you are sending messages to a friend of yours. In the beginning, he replies to you immediately. After a while, he probably gets busy, so he stops to text you back in time. But we also know that wording and typing could take a little time, so we have to wait for a short time before we can assure that he is really busy. The idea is similar. If the sending rate of a rate limiter is greater than its receiving rate, and these situations last for a hysteresis period, then we consider there is a congestion event happening. So, what to do then? We record current sending rates at the saturated sending rate and reduce it then. This is the curve of the qubit growth function we used. Delta t is the elapsed time since the last congestion event, and mij is the saturated sending rate. To be mentioned, I is the client number and j is the server number. So, whenever a congestion event happens, we record the current sending rate as the saturated sending rate, then reduce it to 1 minus beta dot mij. After this, we redraw this curve and growing the sending rate from the y-axis slowly and gradually. If no congestion event is perceived, then the client will probe for a bigger sending rate aggressively again, as is shown in the convex region of this curve. To evaluate CARD and the competing strategies, we implemented a prototype replicated metadata server cluster for simulation purpose. and we used up to 8 servers to measure system scalability. To run the heterogeneous experiments, we crafted a descending setup for these servers. There are 10 clients run on separate machines, launching requests with poison arrivals. The time window is set to 5 milliseconds, and the hysteresis period is set to twice the time window. The multiplicative decrease parameter beta is set to 0.2. For more setup details, please refer to the paper since we cannot run through all the details. We run all experiments trying to answer 2 questions. Do card's rate control mechanism work as expected? Can card achieve better scalability? The answer to both questions are yes. We proved that the rate control process is effective and adaptively guaranteed by this. Loads among servers are balanced under heavy workload as we expected. As a result, card managed to achieve better scalability compared to all the other methods. First, here are examples of the rate control procedure. We visualize the sending rate curve and the receiving rate curve. From these figures, we can easily observe that the sending rate from each client to each server is adjusted adaptively according to the receiving rate. However, we do not know the situations as servers from these figures. So, we recorded the overall arriving rates at all servers. The gray dashed line is the service capacity of each server. The figure on the left side is the overall arriving rates of the heuristic selection method, MOT. We can easily observe that heuristic selection causes severe herd behavior and load oscillations even in the homogeneous cluster. Because of this, the whole system is losing performance. Some servers are extremely overloaded, while other servers are underloaded, even though all requests can be launched at full speed. A data loading job still has to wait for the reply for the last request. As for the figure on the right side, it illustrates how insufficient the congestion-aware feature is. When facing heavy workloads, even though some requests may be suppressed, but a data loading mission is complete way earlier instead. For heterogeneous setups, the round-robin with threshold-based throttling method LESS doesn't do very well as the same as heuristic selection. As for card, we can observe from the figure on the right side that it has all servers bear the load, which is commensurate with its performance. All the arriving rates turn out to be stabilized around this server's capacity. Clients are presuming max performance while avoiding the overloads. Let's investigate the system scalability then. The x-axis is the number of servers, and the y-axis is the overall throughput of the cluster. 2 conclusions can be drawn from this figure. 1. Heuristic selection is the best choice under heavy workloads. The herd behavior and load oscillations brought by it degrade the overall performance. 2. In ideal homogeneous environments, round-robin and card both achieve great scalabilities. This is in line with our expectation. For heterogeneous setups, round-robin is too simple and ineligible. A fixed and even client-side dispatching strategy causes severe performance loss. In contrast, CAR outperforms other strategies and achieves excellent scalabilities with the help of a congestion-aware rate control process. To sum up, today we presented CAR, an adaptive client-side throttling method for replicated metadata server cluster, which is easy and efficient. Briefly, CAR redirect requests from the overloaded server to the underloaded server adaptively when facing heavy workloads. When the load is lightweight, CAR degrades into pure round-robin, which is harmless. For heterogeneous setups, CAR boosts throughput significantly compared to competing strategies, which we believe is our main contribution. So I will conclude here. You are welcome to ask any questions. We will try our best to answer at the synchronous section. Hope you are doing well during this frustrating pandemic.